My name is Shijia Pan. I'm a PhD student from Carnegie Mellon University. Today, I'm going to introduce our work on the indoor person identification through footstep-induced structural vibration. So this is a collaborating work between electrical and the computer engineering department and the civil and the environment and engineering department, with Ningning, Yuqiu, Iran, Peiyong, and Pei. So one fun fact I want to mention before I go to the detail is that the 6 authors here, 5 are female. So guess who is the outlier? So many smart building applications today aiming at providing intelligent understanding of a person's needs and activities ubiquitously. So in that sense, the building needs to learn the identity of the person first. Person identity information can be applied to personalize their services, enhance the security, etc. For example, when deployed in advancing hospital and the nursing home, the system can recognize the patients when they walk and understand each patient's walking area. Such information can help the nurses obtain a better understanding on the patient's conditions. So in that sense, the goal of this project is to achieve ubiquitous indoor person identification. Various of identification methods has been explored. From sensing perspective, these systems can be categorized into mainly 3 types, including vision-based, sound-based, and load-based method. They have been proven efficient under different scenarios. However, each has its own limitations. For example, the vision-based and the sound-based methods are often require human interaction. You may be asked to take off the glass or organize your hair and put your face towards the camera for those vision-based methods. You may need to speak to the microphone to get your voice captured and analysis for those sound-based methods. The load-based method is usually of more ubiquitous usage, but it requires high density deployment to even higher level. And when used for passive sensing in ubiquitous scenarios, the vision-based method may have insufficient sensing resolution problem, while the sound-based methods are vulnerable to the noisy environment. The load-based method has limited sensing range, which will lead to various problems, including high cost in both computation and money. So here, we propose our structural vibration solution. So we noticed that the structure vibrates when people step on it. And based on prior works we surveyed, people's gaits are unique enough for identification purpose. So that means by measuring the structural vibration, we can actually identify people through the unique flow of vibration their steps are causing. Therefore, comparing to the methods mentioned before, the goals of our sensing solution, including ubiquitous, sparse, and of less sensing constraints. So since our system passively monitors people's footstep vibration, it's device-free and interaction-free. So that enables ubiquitous sensing. Our sensors capture structural vibration, and due to the better wave attenuation property in solid, our system can detect individuals in up to 20 meters. So that enables sparse sensing. In addition, when comparing to vision-based and sound-based method, the signal propagation in solid encounters less dynamic noise as interference. So in order to achieve such sensing purpose we mentioned, we propose our sensing system with 3 major components: the flow vibration sensing module, the footstep analysis module, and the decision-making module. So first of all, our vibration sensor, the geophone, captures the floor vibration induced by footsteps. So the signal then are amplified and digitized and sent to the footstep analysis module. The signal induced by footstep impulses are recognized, and the features of these signals are extracted. These features are used for decision making to identify the person. So first, each step is assigned with the ID. Then in order to increase the accuracy for the identification, a trace level classification is conducted to determine the ID. Now let me first of all introduce the floor vibration sensing module. So this is an example of our sensing node. The geophone is used to measure the floor vibration velocity. The vibration induced by footsteps are of very small amplitude. So in order to conduct the further analysis, we amplify the signal in our experiment with an empirical setting of 1,000 times. The amplification setting is actually adjustable for different sensing conditions. Then the processing board digitizes the signal and stores the data. The second module in our system is a footstep analysis module. So signal induced by footsteps are obtained first, then the features are extracted from these signals. Now we are going to talk about the step extraction first. So this figure demonstrates a segment of signal collected from a person passing by one of our sensing nodes. The x-axis is the time in unit of second, while the y-axis is the velocity we measure of the vibration. And from this signal, we are going to extract those signals induced by footsteps. So we first define a step event as the floor vibration signal induced by a single footstep. And then we define a trace as a sequence of step events from a continuous walk of a person. So in order to extract the footstep events from the signal segment for further analysis, we conduct anomaly detection based on the Gaussian noise model as discussed in one of our prior papers. So once the step events are extracted, we conduct feature extraction on them. So before that, we want to understand whether different people walk differently or similarly. For example, person A and person B have different center of gravity position when they walk, and the angle between foot and floor are different. That's quite different in terms of the gaits. But how much difference can be observed in their step events? So to find that out, we plot the step event from these two people in both time domain and the frequency domain. The signal on the left-hand side is the time domain signal with x-axis of time and y-axis of amplitude. While the signal on the right-hand side is a frequency domain signal with x-axis of frequency and y-axis of power. So we observe that person A has smaller angle between foot and floor with gravity kept in the back, and his step event has longer and slower attenuation. While person B has larger angle between foot and floor with gravity leaned back, and her step event has shorter and faster attenuation. And further, clear difference of peak value and position in frequency domain can also be observed from these figures. So the takeaway message of this slide is that we observe variation from step events of different people. So now we already look at the different people, we need to understand that the same person's footstep look consistent. So this plot shows the step events from different random selected traces of the same person. And we observe similarity in the characteristic we mentioned in the last slides. They are both time domain and frequency domain. So with the observation we made, we extract features from both time domain and the frequency domain that include standard deviation, entropy, peak amplitude in time domain, and partial spectrum, spectrum centroid, peak amplitude and frequency, etc. in frequency domain. So such features are used to make a decision on the identity of the person. And we are going to talk about the last block, the decision-making module. So in order to use a step event signal for identification, intuitively we want to assign each step event an identity. So to do that, we use the multi-class SVM to classify each step event based on the feature extracted from the last module. And with some preliminary test, which I'll explain later, we realized that the classification accuracy is not high enough. But we also realized another fact, that there's an important information we haven't used yet, which is all these step events from the same trees should belong to the same person. To use that information, we conduct a trace level classification based on the result of the step level classification. So we obtain the step identity and the confidence level from the step level classification. Then we select the step within a trace that has the highest confidence level as the representative of the entire trace. For example, in this hypothetical trace, the step event with highest confidence level has the identity of person B and the confidence level of 96%. So we assign the identity of the trace as person B with a confidence level of 96%. So based on the result from trace level classification, we notice that many misidentified cases actually have really low confidence level. That means by thresholding on the confidence level, we can distinguish uncertain cases and assign them as unknown. This allows our system to tune the threshold based on the requirement of accuracy and the tolerance of number of unknown ID for different applications. So in order to evaluate our system, we conduct an experiment in the hallway. We used hardware of geophone amplifier and the oscilloscope, and we asked 5 people to walk in, passing by our sensor 20 times per person. We use 80% of the trace from each person as training data and the rest as testing. The experiment results are shown in the figure on the right-hand side here. The x-axis is the confidence level threshold, and the y-axis is the percentage of classification accuracy for the red line, and the percentage of classified cases for the green lines. The solid lines are results for trace level classification, and the dot lines are for step level classification. So from the figure, we can see that when there's no thresholding, the step level classification reaches over 16% accuracy, while the trace level classification improved over 20% accuracy from the step level. And when the thresholding, when we threshold to discard half of the uncertain cases, we have the step level classification reaches over 80% accuracy, while the trace level classification reaches 96.5% accuracy. So we believe such preliminary results are promising, and there's a lot more to explore for more practical scenarios. We want to understand and explore more features in the data we collect, and we want to find the limitation of our system when the number of registered users are increasing. Further, when multiple people are sensed in the same sensing area, we want to simultaneously, we want our system to be able to handle that. We also want to understand the impact of shoe types, different shoe types and floor types on our system. And further, since we are measuring the structural vibration, the environmental variance is going to have big impact on our system. So how to make the system environmental invariance? So we are trying to do that through adaptive sensing configuration. And in the end, we conclude that our system achieves ubiquitous sensing of person identification through structural vibration. The system allows sparse sensing with up to 20 meter sensing range. And the system achieved 96.5% person identification accuracy when discarding half of the low confidence traces. And that will be the end of the talk. Thank you very much. If you have any questions, please let me know.
Okay, let's thank our speakers.